Hey, so it's been a while since I've done any videos, but what I kind of want to do is something a little bit more complicated than I've done in the past, something a little bit more elegant, and that is deriving the quadratic formula. Now, the quadratic formula is something we all know and love. Maybe you don't have it quite memorized, but it comes quite in handy when you're solving quadratic equations for a variable called x. So this is what we call standard form for your quadratics. So when ax squared plus bx plus c is equal to 0, the quadratic formula gives us the solution as x equals, it's negative b plus or minus the square root of b squared minus 4ac, and this is all over 2a. A, b, and c are all just numbers. And normally I like to call those constants. I mean, they're constants. They're not variables. We're not trying to solve for them. We're only trying to find the value of x. But a, b, and c are all just numbers. This video is about how did they come up with quadratic formulas. Is it magic? Why does it work every time to solve a quadratic? It's not magic. Well, I guess there's different ways to think of what constitutes magic. But we can demonstrate this using some pretty simple algebra tools. The only thing is it's very abstract, meaning we're working with mostly letters and symbols rather than numbers. But they mean numbers. And let me make one other thing clear. The only variable here is x. We're trying to solve for x. We want to find out what's the value of x. A, b, and c are arbitrary constants, not variables. Okay. Now that we've gotten that down, let's see how we can manipulate this equation. The whole idea of quadratic formula lies in completing the square, but we can't complete the square if we have a leading coefficient. The good news is we can always get rid of a leading coefficient by dividing it out. Remember your rules for algebra. Whatever you do to one side, you have to do to the other side. If you divide something from one term, it also gets divided from the other term. That's actually due to the distributive property. And so, this cancels. We're left with x squared plus this middle term is b over a as your coefficient for x. Constant term is c over a. Here's the beauty of this. Here's why we could have done that. 0 divided by a is still 0. So we didn't change the right-hand side at all. I mean, we did. We divided by a, but it remained 0, because if you divide 0 by anything, you still get 0. So our goal is to complete the square on the left-hand side. Let's go ahead and get the constants to the right, the regular old numbers. And in this case, it's just the value c over a. Subtract it from both sides. We end up with x squared plus b over a x. And what we want to do, because we have an x squared term and an x term, is we want to complete the square. Now we want to find out what value can I add to that that'll make that a perfect square. Then we want to express it as a perfect square. I'll get to that in a moment. On the right-hand side, what's going on, this is still equal to negative c over a. So completing the square says take half of the middle term, in this case b over a. Half of b over a is just b over 2a. The number which actually completes the square, the constant that we have to add, is half the middle term squared. So here's half the middle term, and then it's being squared. Still equal to negative c over a. But we have to remember to balance our equation. On the left-hand side, we added this constant. We chose to add that constant to complete the square, to make it look like this. We chose to add that. So we have to also add it to the other side, b over 2a squared. Now, how do I know that this was the right strategy to use so far? Well, because if I have x plus some number and it's being squared, all I have to do is take the square root of all this junk. If I take the square root, I can solve for x pretty easily. Let's focus mostly on the right-hand side for now. Let's keep this as negative c over a. Let's simplify this using properties of exponents. So this squared gets applied here. The squared also gets applied to the denominator. It's going to be plus the top is going to look like b squared. And the bottom, or the denominator, is going to be a, the entire quantity, 2a squared. Make sure you know how to do this. 2a squared. We're not just squaring the a, we're squaring everything. So there's another property of exponents. The squared gets applied to both of those. So 2a in parentheses squared is actually 4a squared. That's what our denominator is. So now we have a rational expression on the right-hand side. We need a common denominator so we can add those two, and just basically express them as one large fraction for simplification reasons. So thinking about a common denominator here is you have to see what do you have to, we want to make the denominators look the same, be equal. This one is a 4 times an a times another a. This one's just an a. So, but if I multiplied this by a and then 4, it would look just like this, 4 times a times a, 4 squared. So I can do that on the bottom as long as I also do it on the top. Multiply this by 4a. Right, so let's rewrite this. This is negative, and let me switch the order here so it looks more like how my end product is going to be. This is just 4 times a times c plus b squared. And it's over one single denominator, 4a squared, the common denominator. Okay, remember that all this is still equal to x plus b over 2a squared. And we're trying to solve for x. I'm going to scroll down a bit. We are set up to take a square root. Here's when we do it in red. Take the square root of both sides. We want to get x by itself. We want to isolate x, solve for x. As taking the square root of this is not going to give me x, but it's going to give me what's underneath the radical here, x plus b over 2a. That is equal to all this junk. Remember another property here of square roots. That whole thing. When you take a square root, you're really taking the square root of the numerator and the square root of the denominator. Let me write the numerator like this, switching the order here, but keeping the signs. It's a positive b squared. It's a minus or a negative 4ac. And when we take a square root like that, we always have to remember to put a plus or minus sign next to that value. And then we're also taking the square root of the bottom. The square root of 4a squared. Moving back to our original column here, we can re-express the right-hand side now as plus or minus the square root of b squared minus 4ac over square root of 4a squared is 2a. And we're in luck. We're in a lot of luck because this has the same denominator as this constant that's being added to x. So in order to solve for x, we just have to subtract b over 2a from both sides. But that's not a problem because they have the same denominator, so they subtract very easily. This cancels. Finally, we have x equals, we're doing this numerator minus this numerator, and let's rearrange the terms. I don't want to skip steps here, so let me show you know what this is. We're doing plus or minus the square root of b squared minus 4ac, and that whole thing is minus b over 2a. That's what happens when we simplify the rational expressions there. However, quadratic formula doesn't look like this. It's got the negative term in front for whatever reason. Negative b, and then everything else follows. Remember to look at the signs before terms. So if this is positive or negative, or we can say plus or minus, b squared minus 4ac over 2a. Final product or final result is the quadratic formula. So, being an algebra student, if you were ever curious about where they came up with that formula, no, there's a rhyme and a reason behind everything in mathematics.